Hi, I'm Dr. Incognito. In this video, we're going to compute limits analytically. In the first example, we're going to look at the following limit. The limit as x approaches 2 of x squared minus 4 divided by x minus 2. Our first approach when trying to calculate this limit is to simply plug in the number 2 for x. Upon doing so, in the numerator, we get a 0, 4 minus 4, and in the denominator, we also get a 0, 2 minus 2. This is a very special form called an indeterminate form. And this form arises quite frequently when trying to calculate the slope of a tangent line to a graph. In fact, this limit occurs when we try to find the slope of the tangent line to the curve y equals x squared at the point 2, 4. So to handle this situation, we're going to factor and cancel. So the limit as x approaches 2 of x squared minus 4 over x minus 2 is equal to the limit as x approaches 2 of the numerator here factors as a difference of 2 squares, x plus 2 times x minus 2. So now the x minus 2's cancel, and we're left simply with the limit as x approaches 2 of x plus 2, which is equal to 2 plus 2, which is 4. So by factoring and canceling, we can compute the value of the limit. In this case, the 0 over 0 indeterminate form has the value 4, and the slope of the tangent line here is 4. In our second example, we will investigate the limit as h approaches 0 of the square root of 9 plus h minus 3 divided by h. And this limit occurs when trying to find the slope of the tangent line to the curve y equals the square root of x at the point where x is equal to 9. The point 9, 3. And just as in the previous case, if we try to plug in the value 0, then in the denominator we obviously get 0. And in the numerator, if you let h equal 0, you get the square root of 9 minus 3. Well, that's also 0. So we get the 0 over 0 indeterminate form. In this case, to resolve the matter, we're going to want to rely on something called the conjugate radical. So the factorization formula that we used here, x squared minus 4, comes into play in a very significant way here. A squared minus b squared factors into a minus b times a plus b. These would be conjugate expressions. So we want the conjugate radical expression here, which would have a plus in between. So if you look at the square root of 9 plus h minus 3 times the square root of 9 plus h plus 3, if you multiply those together, that looks like the right side here. You're going to get a squared minus b squared, which is 9 plus h minus 3 squared is 9. Notice that when we square the square root of 9 plus h, we get 9 plus h without the radical. So 9 plus h minus 9 will simplify to h. So let's take advantage of this computational device to compute the limit. So we have limit as h approaches 0, radical 9 plus h minus 3 divided by h. What I'm going to do is I'm going to multiply this fraction by the conjugate radical over itself. So the square root 9 plus h plus 3 divided by itself, and that's necessary because I'm just multiplying by 1, so I'm changing the way the expression looks without changing its value. And now we've already done the computation of the numerator. That was here. When you multiply those numerators together, it simplifies to h. And in the bottom, in the denominator, we have h times the square root of 9 plus h plus 3. And now the h's can cancel. And then once the h's cancel, we can plug in 0 for h. So canceling the h's leaves us with 1 in the numerator and the conjugate radical in the denominator, and letting h be 0, we get 1 over the square root of 9 plus 3. That's 1/6. 1/6. So the slope of the curve, y equals the square root of x, at the point 9, 3, if you draw that tangent line in there, the slope of that tangent line is 1/6. Okay, so one other example, using analytical methods to compute a limit. This time involving a complex fraction. The limit as x approaches 3 of 1 over x minus 1 over 3 quantity over x minus 3. So this is a complex fraction because it contains fractions within the numerator, in this case, of a larger fraction. So in order to resolve this situation, again, if you let x equal 3, you're going to get 0 over 0, the indeterminate form. To resolve this situation, we're going to want to manipulate fractions a little bit. So first, if you're subtracting fractions, a over b minus c over d, the common denominator is bd. And in the numerator, in order to convert this to the common denominator of bd, you'll need to multiply by d over d. And in order to convert this one, you'll need to multiply by b over b. So here you'll get an AD, and here you'll get a BC. So it's AD minus BC over BD. And then once we do that, we're going to have a fraction of the form A over B over C. And that's A over B divided by C, which is A over B times 1 over C. Division is multiplication by the reciprocal, and then this is A over BC. Multiplication of fractions is simply straight across, A times 1 and B times C. So if we apply those types of calculations in this example, we get the following. The limit as x approaches 3. First, subtracting the fractions, so we'll leave the denominator alone. The numerator will have the following fraction. The denominator of that fraction in the numerator is 3x, and the numerator of that fraction will be this times this, which is 3, minus this times this, which is x. So 3 minus x over 3x. That's our numerator fraction now after combining these two and divided by x minus 3, just leaving that alone for the moment. And that brings us to this second stage. So this is equal to the limit as x approaches 3 of, just going right from the form A over BC here, there's A, B, and C. So it's 3 minus x over 3x times x minus 3. And now the final step is to cancel. And here, if we had x minus 3 over x minus 3, we would cancel those out and we would be left with 1s. That's 1 over 1. So here we have to make the observation that 3 minus x is the opposite of x minus 3. Those are opposites, so this cancels to be minus 1. So these cancel, leaving minus 1. Because these are opposites. The numerator and denominator here are opposites. So we have limit x approaches 3, negative 1 over 3x. When we plug in 3, we get negative 1/9. Negative 1/9. And this limit also comes from finding the slope of a curve at a point. The curve is y equals 1 over x. At the point, x is 3, and so y is 1/3. Point 3 comma 1/3, the slope of the tangent line right there, the slope of the tangent line, you can clearly see in the picture that it's negative, and according to our calculation, it is negative 1/9. Okay, so there's a look at computing limits analytically using algebraic methods. Thank you for watching.